Hello and welcome to this clip going through the 2018 Cambridge Chemistry Challenge paper, this time question 2. So like it says on the front of the paper, it's meant as a challenge and some of the areas that you'll come across won't be familiar to you. This is expected. So don't worry if you come across something that you haven't seen before. They'll give you enough information in that case to get you started. You need to, however, have a problem-solving, reductive approach to the question as opposed to remembering or recalling masses of information from your course so far. And likewise, as you'd expect, you'd need to make sure your mathematical techniques are quite good. So when you're dealing with units, you need to apply them and convert them across, or significant figures where specified. This is in common with regular A-level chemistry papers. For example, using appropriate significant figures would mean using a level of sig figs that are roughly equivalent to the least sensitive that are found in the question. Now, you'd also get provided with a periodic table, and if you look at some of the values, they are to a greater number of decimal places, the values for relative atomic mass, that is. So always use these values instead of the ones you may remember from your exam board's own periodic table. You may already have some in your mind for common elements like carbon, chlorine, oxygen, for example. If you've been doing past papers and using your own exam board's periodic table quite a lot, try not to use those values, but use these ones instead. Now, as is common with all Cambridge Chemistry Challenge questions, they give you some context at the start that is a real-life application of the chemistry you're about to be asked on. So you'll normally find that the very first part of a question is going to be easy and accessible if you've done something you've done before, just to get you moving. This is in order so that you don't feel that you're stuck. So once you're up and running, then you're more likely to be able to face the more difficult sections later on with a bit of confidence. So let's do part A first. It says to draw the structural formulae, not the skeletal or the display, but the structural formulae of propanoic acid and 2-methyl-butanoic acid. Now, although they technically allow the displayed formula in the mark scheme, I'm providing the structural formula because that's something they're usually quite strict about in actual regular A-level questions. So even though they might be slightly lenient on this particular occasion, if they say structural formula in a regular A-level paper, you must put the structural formula, not another version. But if you're told to do the structural formula or you're told to do the displayed formula or whatever, you need to demonstrate that you can follow the instruction. So then it wants you to give the general formula for saturated aliphatic carboxylic acid, so therefore one that has the COOH functional group attached to a straight or branched chain alkane. So bearing in mind that an alkane is CnH2n plus 2, in a carboxylic acid of the kind that they've described, you'll take away one of the hydrogens and replace it with a COOH. And when you're thinking about it mathematically, you might be tempted to include the carbon in the COOH within the CN part. You don't do that because the COOH in itself is a functional group, so that needs to be in your general formula to show the person reading that the COOH is actually part of a functional group. So in part C, it talks about a sweetener in the form of salt A, and it forms a simple hydrated crystalline salt. So we need to remember that when they say hydrated, that means it contains water of crystallization in the form XH2O in the formula. Okay, so the first part wants you to calculate the percentage by mass of the metal ion M. So what you've got to do is to subtract the sum of all the other percentages from 100. So that gives us 54.64%. So I start by dividing the percentage by the atomic mass. And the next thing I've got to do is divide each of those by the smallest. Now if I do that, it still doesn't solve the problem entirely because I still have ratios to deal with, as in decimals as opposed to whole numbers. But if you look at 1.75, that can be multiplied up by 4. So, if we take 2.97 to be roughly 3, and we multiply 1 by 4 as well, do this basically multiply by 4 throughout, that gives us 4, 12, and 7. So now we can give the empirical formula as MC4H12O7. So now we need to identify the metal that forms ion M. So to do this, I'm going to put some space up in the top right-hand corner, so if you can follow up there, that'll allow us to continue. So if we take the C4H12O7 part of the molecule and separate that away from the metal, that in itself has 172.14 grams per mole. So if we take the percentages provided by the question and add them up for carbon, hydrogen, and oxygen, this accounts for 45.35% of the mass of the salt. So that must mean that M accounts for 54.65 of the mass. So now we can calculate the relative atomic mass of M. So if we work on the assumption from our empirical formula that only one ion of M is responsible for this, then we can calculate the relative atomic mass of M. So putting the numbers gives us 207.4 grams per mole. So it mentions gentle heating, and the solid, salt B, can be assumed to be the anhydrous version of salt A, because you can see there's still some carbon, hydrogen, and oxygen present, but this time that would be bound up in COOH groups, so it would be a carboxylate of some kind. What I mean by that is would be a salt of a carboxylic acid. So we can use the same technique as before, in other words, the percentage divided by the AR. So using the same technique as before, you can divide by the smallest and also convert to whole numbers. And that'll give you the empirical formula of the hydrated salt. Sorry, I meant to say the anhydrous salt, but that gives you PbC4H6O4. So by comparing it with the hydrated version, you can see that there's 3 molecules of water of crystallization that have been driven off. So now we can write out the equation that the second part of part D wants you to do. So you could write it in pure structural form. You could also write it in molecular form. You could even write it broken up with the .3H2O on the left-hand side for your hydrated version if you wish. I think there's several different ways you could do it from the mark scheme. Okay, so then it wants the oxidation state of the metal ion M in salt A. Now at this particular point there'd been a communication from the C3L6 exam board to say that it meant to say salt B in part III, not salt A. But I don't think it makes a difference because it would still be +2. Because the difference between salt A and salt B is the water of crystallization, which has no bearing on the oxidation state of the metal ion. So the way I can work this out, that it's +2 and not +4, which is the alternative oxidation state for lead, is that in the formula of the anhydrous salt, because of the 4 oxygens, there's only a maximum of 2 lots of COOH. So each carboxylate group would have a -1 charge. As it deprotonates, it loses the H. So 2 of them would each lose a hydrogen, and then 2 of them would be able to ionically bond with 1 Pb2 plus ion. So that must mean the oxidation state of the lead in this compound is +2. So this would suggest that the carboxylate salt would be lead ethanoate. So therefore the acid would be ethanoic acid. Okay, so now we can move on to part E. So it mentions hydrogen peroxide in aqueous form being reacting with carboxylic acid in the presence of the metal to produce salt B. So hydrogen peroxide is generally an oxidizing agent. It can sometimes be a reducing agent. It can do either because it disproportionates. So that means that the oxygen is simultaneously oxidized and reduced. So one of the oxygens is reduced, the other one is oxidized. So we need to think about what's actually going on in this particular case. So we start by putting in the mole quantities, the molar stoichiometry of the lead, the ethanoic acid, and the hydrogen peroxide. Now, remembering that the salt contained 2 ethanoate ions, we need to put 2 moles of ethanoic acid in. So remember that the lead cation, your Pb2+, and the 2 ethanoate anions form a neutral salt, so there's no charges needed in your equation, even though I put them in the previous, just to show you where the charges come from. Now, I mentioned disproportionation here. I said it nearly always acts in a redox capacity, but disproportionation. If it does so, normally oxygen is given off. But in this particular case, you'd have to have something that the hydrogens turn into. So the hydrogens would turn into water. So the oxygen that would normally be given off when H2O2 sort of decomposes into water and oxygen, that isn't actually being produced at this particular juncture. So this time around, we're just producing the water. So what's happening is the ethanoic acid is being oxidized because hydrogen is being removed from it. So that's another way of thinking about oxidation, the removal of hydrogen. So this, in this case, the H2O2 is acting as an oxidizing agent. So now we'll go to the next page on the question and we'll move on to part F. So before we start looking at answering part F, let's have a look at the information they've given. So they're talking about how a carboxylic acid can react with a base to form a carboxylate anion. So in the carboxylate ion, it's just slightly beyond A level. When you do carboxylic acids in your second year, you may or may not have this explained to you by your teacher. Some teachers do it, other teachers don't. I like to do it with my students because it just gives a little bit of extra information. And by the time you come on to do that, you'll have come across the idea of delocalization of electrons. So what's happening is the C double bond O and C single bond O, they kind of alternate positions. So the overall result is you get a sort of delocalized negative charge. So it's the pi electrons that delocalize. So when you do benzene, it may be that you've started doing it. If you do aromatic chemistry, then you'll know that there are delocalization of pi electrons throughout the aromatic structure, the aromatic ring. So in this case, there's a delocalization between the C double bond O and the C single bond O. So the C double bond O could be the bond poking out the top, or the C double bond O could be the bond poking out the bottom. It's about 4 o'clock in the little diagram. So you can also look at how the delocalization is set up by using curly arrows, and you can see that quite clearly on the paper already. But basically, it's the same chemical species that's being represented. They're not 2 different structures. It's just the position of the C double bond O relative to the C single bond O swaps around. Now, sometimes the protons that are attached to a carbon atom can be acidic. Now, in COOH, you're usually used to the protons being attached to an oxygen, as in the OH part of COOH. But occasionally, the protons attached to a carbon can be acidic, and therefore they can be lost to form an increase in concentration of H+ in a solution. And the example they give is the presence of carbonyl groups makes the protons attached to the adjacent carbon much more acidic than in an alkane. So what that means is those protons that I've now highlighted are more likely to come off as H+ because of their proximity to a C double bond O. So what they want you to do is draw the structure of the anion formed when a base removes one proton from ketone C. So you can do two versions where the charge is localized, or another version where the charge is delocalized, just like it shows you in the diagram. Okay, so let's look at part G now. So it says here that protons on a carbon atom that is adjacent to two carbonyl groups are particularly acidic. So in methyl 3-oxobutanoate, the protons at position B are more acidic than those at position A. So just to explain what they mean by that, in position A, you're only adjacent to one C double bond O group. But looking at position B, you've got C double bond O either side of where you are, so basically position B is more acidic. So it's more likely that a proton will be lost from position B. So they want you to draw two representations of the resulting anion in which the negative charge is on an oxygen atom. So if you look at the circled structure from the previous question, that's the kind of thing that they're after. So I've stuck down two possibilities. It shouldn't be too difficult to see that if you've got two carbonyl groups either side of your position B, all you have to do is put the oxygen on either side of it. I just realised what I'd forgotten to do. Whoops, just give me 2 seconds. Double bond in there. Yeah. Okay, so now let's go on to the next part of the question. So in this new section, it talks about a chemist called Karl Claus from the German chemical company Hoechst. I apologise for my improbable pronunciation, but Hoechst AG. Having contaminated his hands with some of the chemicals he was working with, he licked his fingers to turn over the page of a book, and then his fingers tasted sweet, and he discovered by accident an artificial sweetener. Now the synthesis of this sweetener D, involves a reagent called a diketene. Now it says there that it won't be familiar to you. Just explaining what Nu means. Nu is a nucleophilic atom of some kind. It could be oxygen, nitrogen, for example, bonded to a hydrogen atom. So if we treat Nu as having lost a hydrogen as it bonds into a diketene. So you can see it's bonded to a hydrogen, and then when it reacts, it's not bonded to a hydrogen. So you can see that in the final product there's a hydrogen that is actually drawn in on the skeletal formula. So putting a little bit of common sense together, it's possible, is it not, that the hydrogen could have ended up down at the bottom of the molecule. Just a thought, looking at what the molecule is now compared to what it was before as a diketene. Now it says that on the structure of the diketene in your answer booklet, circle the atom in diketene that is attacked by the nucleophile. So thinking for a second about nucleophilic attack, it can only take place if there's an electron deficient atom somewhere. So what will tend to happen is something like this. So the lone pair on the nucleophile will be attracted to a delta positive carbon, and then the second curly arrow coming off the double bond will be the breaking of the pi bond, and then an electron pair goes onto the oxygen. So you'll be doing a mechanism like this in your second year called nucleophilic addition, maybe even nucleophilic addition elimination. In your first year, you probably only come across nucleophilic substitution, but still, in nucleophilic substitution, you'd have something like that. So from your first year knowledge, they're expecting you to have a bit of a head start by thinking about it in that way, so then you can apply it across to this particular structure. Now, I only say this because when I marked my own students' scripts last year, I found that very, very few people actually managed to get this particular question. They struggled a lot. It could be that by this point they were tired. It just starts to get quite hard and demanding. This is quite an applied section of the question as a whole. But if you take it in its isolation, it's not too difficult to work out what might be happening. So they ask you to circle the atom that is attacked by the nucleophile. So I would say that carbon is the one to go for. So let's now go down to part I. So here we've got an organic synthesis for producing sweetener D. And they want you to work out, first of all, what does compound E act as in this synthesis? So looking at the formula of compound E, the presence of chlorine and oxygen means that you've got atoms with lone pairs. And as we just talked about, atoms with lone pairs can behave as nucleophiles. So I'm going to go for nucleophile on this one. So then they want structures for compounds E to G. So looking at each transformation at a time, let's start with compound E. Now compound E involves the reaction of a phenol, which is that functional group. Now a phenol can behave as a weak acid by losing that proton, that H, on that OH. So the base in question is KOH. So what would happen here is the proton comes off, reacts with OH minus to make water, and the K plus goes on to the oxygen. So now we can move on to compound F. So looking at the formula of compound F, it's clear that K is removed. Two reasons. You've also got the KCl as a second reason. Obviously there's no K in the compound F formula. So the species SO2Cl2 must replace K on the structure of E. So now we can move on to compound G. So looking at the difference in the formulae of F and G, in the same way we've been able to deduce E and F so far, you can see that there's one nitrogen and two hydrogens. And furthermore, there's one chlorine removed. So you can see what's happened. You're putting an NH2 on instead of the Cl. So you can see going from G to H, you've got a diketene reaction. So I've left the diketene sort of concept up at the top of the screen so we can try and apply it to this. So what we're looking for is a nucleophilic atom that has a hydrogen attached. So you can see what's going on. We've got our nitrogen that can play that role. So looking at our diketene and a nucleophile, we can treat the nucleophilic atom as nitrogen. So that allows us to suggest a possible structure for compound H, moving on to part K. And it says, circle the most acidic proton on your structure for compound H in the answer booklet. So I've added, instead of circling it, I've added them in on the clip. So either of those two hydrogens will do. And the reason for that is they sit between two C double bond O groups. They've got a C double bond O carbonyl group adjacent on both sides. And then it says, the final product, sweetener D, contains a six-membered ring. It asks you to suggest a structure for sweetener D. So if you look at the formula of sweetener D, it no longer supports the idea of a six-membered carbon ring. So the aromatic ring that's been in all the structures so far has to go. And also, if you look, you'll get the phenol, the potassium phenoxide produced at the end. So we have to be a bit creative about what we're going to do here. So I'm going to create some space at the top right of the screen to try and come up with something. So we know that we've got the SO3 group, or something similar to it, because we've got the sulfur atom and we've got 4 oxygens, 3 of which will be used up in the sulfur. We know that the sulfur is bonded to a nitrogen. So I'm looking at the other part of compound H. I'm ignoring the bit with the 6-membered carbon ring with the chlorine coming off the left-hand side. I'm looking at the bottom right-hand corner of the screen and constructing something from that. So, looking at the very bottom of the screen where you have the 2 carbonyl groups, it's possible that one of them could be included. So let's pop that one in. That's the one next to the nitrogen. Now, let's bring this round like so. Remember those structures we were looking at earlier, and where we had that mechanism described. And let's now bring a bond down there, and a methyl group off there. Now, not forgetting we've got to have 2 H2Os that come off here as well. If you look over on the left-hand side of the screen, at the very bottom of the organic synthesis, when you make potassium 4-chlorophenoxide, you also have 2 H2Os. So that's where the spare hydrogens could be used up as. Excuse me. So do we have a 6-membered ring here? Yes, we do, because I've highlighted the atoms that make up the 6-membered ring. So I think that gives us our structure. So now what we can do is move on to the next question, next section, section 3, which is part L. So no surprises here for guessing this is the mathematical section of the question. So again, there's quite a lot of text with a graph, so let's just highlight that and have a think about what it's telling us. So it tells you that nitrogen-containing compounds in urine, if you do biology, you'll probably be thinking about things like urea or uric acid, can react with chlorine in swimming pools to form compounds that are volatile and irritating to the eyes and respiratory system. So these compounds are called chloramines. They've got chlorine in it, an alkyl chain of some kind or structure, and an NH2 group. They're not very good for you, and sometimes people who use swimming pools quite a lot suffer from irritation to the eyes afterwards. It's not actually the chlorine itself that's doing it, it's the chloramines. And obviously, not thinking about it too much, where's the urine going to come from? Well, you can guess. Not very pleasant, so hence why it's actually a public health hazard to shall we say, unload in that way in a swimming pool. So moving on swiftly, it says, a marker for the quantity of urine in the pool is therefore desirable. Consumption of sweetener D is widespread in North America, and as is excreted in the urine, it's ideal for use as a urinary marker in this region of the world. So the concentration of it in water sample can be determined using mass spectrometry, and what happens is the water sample is spiked with a known amount of deuterated sweetener D. So essentially what this means is that one or more of the hydrogen atoms in the sweetener are replaced by an isotope of hydrogen called deuterium, where you've got an extra neutron in the nucleus, hence 2H or instead of 1H, but it's often just called capital D for short. So what happens is the intensities of the equivalent peaks from sweetener D and then the spiked version, as in the deuterated version, are compared. And you can draw a graph with the absorption on the x-axis for sweetener D and absorption on the y-axis for deuterated sweetener. And generally what will happen is you'll get a straight line, and you can extrapolate. So from the concentration of the deuterated sweetener, you can work out what the concentration of the sweetener D would have been. So I've put in a couple of red lines just to show you how you can extrapolate the concentration of the deuterated sweetener that's picked up by mass spectroscopy compared to the actual sweetener from people's urine in the pool that is on the x-axis. Just a quick example, and obviously it gives you the y equals mx plus c formula, so the dy over dx is 0.098, the gradient is 0.098. So to work out the concentration in nanograms per decimeter cubed, you need to multiply nanomoles times the MR. So to an appropriate number of significant figures, in this case 3, you've got 8.57 nanograms per decimeter cubed. Right. So the next part M. So to calculate the concentration of sweetener D in the pool water, I need to use the equation for the calibration curve, which is y equals mx plus c, or at least in y equals mx plus c format. Now the concentration of the sweetener D is the x coordinate, so x has to be the subject. So rearranging, it's x equals y minus c over m. So the concentration would be 7.806 nanograms per decimeter cubed, but the sample was diluted 20-fold, so the concentration is 20 times greater than that. Okay, so moving on to the final two bits. So for part N, it's quite straightforward. You apply the same technique as for part M, but they give you the peak area ratio is different this time. It's 2.41, and the dilution factor is times 10 to the power of 5. So sticking to 3 sig figs, we get 247,000 nanograms per decimeter cubed. So to calculate the concentration of sweetener D in the urine, and therefore work out the volume of urine in the swimming pool in decimeters cubed, you need to take the sweetener D concentration from the pool and minus from that the sweetener D concentration in city water. So that gives us 147.43 nanograms per decimeter cubed. So the pool volume in decimeter cubed is meters cubed times 1,000. So remembering that the question told us that the volume of the swimming pool from which the water sample is taken is 840 meters cubed, multiplying that by 1,000, you get 840,000. I've left out a 0, give me 2 seconds. So 840,000 decimeters cubed. So the volume of the urine is the mass of the sweetener divided by the concentration. So to work out the volume of urine, you have to get the mass of D. So that's the total mass of D that's present in the pool. So multiplying the concentration of D times 840,000, you get 1.239 times 10 to the power of 8 nanograms. So dividing the mass of D in total by the concentration of D in nanograms per decimeter cubed, you can calculate that you've got 50.1 decimeters cubed. So that takes us to the end of this clip. It's been a bit of a long one. It was actually quite a hard question as it turned out. But hopefully it's a useful application and a slightly amusing one at the end. So until next time, thanks for listening and see you soon.